We come to the next session, and the next session gives us a colorful picture. We will continue with technical issue, something which must not be mixed up with handwritten text recognition, but is different. It's part of pattern recognition, but it's different. It's dealing with automated writer identification and its use cases for archival documents. The speaker is Stefan Fiel. He's coming from the Technical University of Vienna, from the Computer Vision Lab, as some other colleagues are here in the room as well. And I'm very happy that this group is part of the READ project, and they have a lot of experience in this domain. And Stefan was born in Feldkirch in Austria. He studied at the Technical University of Vienna, received a master's degree in visual computing in 2010. He worked at the Computer Vision Lab in several projects, among them DIR, document information retrieval, where his task was writer identification and writer retrieval. Currently, he's writing his PhD thesis with the topic New Methods for Writer Identification and Retrieval, and his research interests are cultural heritage application and document analysis applications. So, thank you a lot for coming.
Thank you very much for your introduction. As Günther already said, the topic is automated writer identification and its use cases for archival documents. And first of all, I want to clarify what is the topic writer identification. What do we understand when we are talking about writer identification? And writer identification is the task of determining the author of a sample handwriting from a set of writers. So we have here, I illustrated it here, we have a database where we have a couple of documents, and we know the author of each of these documents. Then we have a query document, and the system tells us the identity of the writer. In contrast to this, but it's also covered within the task of writer identification, is the writer retrieval. And writer retrieval is something similar, but a little bit different. With writer retrieval is the task to obtain all documents of one writer out of a set of documents. So again, we have a set of documents, a database. The authors do not need to be known in advance, or do not need to be known at all. Then we have a query document, and the system makes a ranking of the documents in the dataset according to the similarity of the handwriting. And then the system returns a ranking of the document which are probably or which are written by the same author like the reference document. So, of course, there are several variations of handwriting. Schumacher and Bulaku defined 4 of them. So we have affine variations where we have different slants, we have shearing and, let's say, a little bit rotation. We have allographic variations where not each character is written the same. So maybe because of the countries, in different countries sometimes some character changes. Then we have a new biomechanical variability, so that the words are not necessarily always written the same. So if you write a text and it contains a word several times, then the appearance of the word is always slightly different. And the last thing they have is a sequence variability, but this is only done for online handwriting. So you write on a tablet, and then we also have the stroke order and so on. But of course, for archival documents, we do not have these additional information, and we have to rely on the image itself. Now I want to talk a little bit of some methods, so we'll present some methods of writer identification, how other groups and our group try to solve this problem. And I took here a rather old approach, it's nearly 13 years old, from Bulaku and Schumacher. And I took this because it influenced the writer identification, so the methods of writer identification for the next years. And it's also quite easy understandable for humans. So what they are doing is they analyze the character itself. So they have here the character, then they analyze the contour by calculating the angle of the contour. And so, as we can see here, they can then build up a histogram out of these angles. And as you can see here, 2 samples. This feature is influenced by the slant of the writing, and it has been shown in previous works that the slant of the writing is also a good feature for identification. Then the next feature they introduced was the contour hinge, which is let's say, something similar, but instead of calculating one angle, they calculate two angles, and so they can build up a 2D histogram of these angles, and instead of only, let's say, describing the slant and so on of the writing, they also extract the curvature of the character, so how curved the writing style is. And the last feature they use is direction co-occurrence, and this time they calculate the angle here, searching for the next pixel in the horizontal direction, but also in the vertical direction, and calculate the angle there. And so they have something like a measurement of the roundness of the character. And as I said, this work is rather old, but influenced a lot of writer identification methods. And now I come to a few modern ones. For example, Li and Ding, they introduced the grid microstructure feature. Actually, this method was the winner of the ICTA 2011 writer identification contest. And as workflow, they have here a text written. So then the first thing what they are doing is they binarize it, and then they are looking for the edges. So they make a simple edge detection method, and then they have the edges, and then they analyze only the edge pixels. And this is done by floating a grid and moving it around the edges. So for example, we have here one edge point, then it would look like this if we zoom in there, and then they use a grid and use the center pixel to describe the neighborhood of this pixel. And this is done by using three criteria. First of all, they just count the occurrences of how many pixels are within the same layer of a connected component. The next criteria is when there is one layer difference, and the third criteria is 2 layers difference. And so they can build up a 2D histogram according to the pixel pairs, how often they occur on the edge. And so they can build up a histogram, and they look like this. We have here 4 sample texts. 2 of them are from the same writer, so these 2 are from the same writer, these 2 are from the same writer. As you can see here, the 2D histograms, they are calculated on this portion of text. And now we can use the difference of these histograms for writer identification. So here we have the difference between the 2 texts of the left writer, and you can see there is only a small difference, and also on the right-hand side we can see the difference between the 2 texts which were on the right-hand side. But if we take the difference of the same 2 texts from both writers, then we can see that the histogram is rather high, and so we have a high dissimilarity, and this can be used for writer identification. The next method is by Rajiv and Dorman, and actually this is the winner of the ICTA 2013 writer identification contest, and they use the contour gradient descriptor. So we have here, they are searching for connected components, which is here mostly, or often it's a word because the characters are connected, and then they try to segment the word into, they say, characters, something similar than characters. You can see here they use a vertical cut method. You can see here there's a sliding window. The red area, the connected component must not be cut. And then they are looking for a possible cut where there is the lowest energy. Lowest energy means there are not very much edge pixels, so that we just cut somewhere where there is only a few pixels of text. And so here they are cutting out the GR, and then they make another cut before the T. And then they start to describe these character-like segments using the contour gradient descriptor. And this is quite easy. They just calculate the gradient, which is actually something like the angle of the contour at every point. And so they can build up a histogram and a feature which look like this and can match this feature with features they've already seen. And so they can build up our current histogram, and this histogram can then be used as a feature for writer identification. The next method I want to present is our method, or one of our methods. So we use SIFT features. SIFT features is like they are calculated, they are automatically located mostly on endings of the characters, on crossing of lines, when there's a lot of curvature in there. And they look like this, and they describe the neighborhood of this location. And the next thing is the scale invariant. So if there is, so for example, the small rings mean that they're only describing a small neighborhood, and the big rings mean they describe a large neighborhood. And then we generate also occurrence histograms and then use the chi-square distance. So at the end, I will show this in more detail in the next slide. At the end, we have a histogram like this, and then we can use this histogram for writer identification, and this histogram should be similar if the same writer has written this text. So, as I said, first of all, we calculate something called vocabulary. So we have here the feature space in 2D illustrated. Of course, we use more dimensions. Then we take some training images, which should contain text written in the same with the same alphabet, like the ones we try to identify afterwards. We calculate the sift features on one text, put them into the feature space, make it for the next training document, also for the next, and so on and so on. And then we have here the features in the feature space, and then we divide the feature space into cluster center using k-means. It's just a simple clustering. And then we have a description of the feature space, a partition of the feature space with cluster centers. Now, if we want to identify a new text, we have here two words. We calculate the sift features on the two words, put them into the feature space, and then look for the closest cluster center, and so we can generate a histogram. So, for example, for this sift feature here, it's located here in the feature space, and this bin is raised by 1. The problem here, and this is the next method we use, is that we have an improper description of the feature space. We can say it like this, because we have strict boundaries, and so we just use GMMs, Gaussian mixture models, for the separation of the feature space, so that we also, for example, this feature, we can calculate the influence of these points to this feature, and so we get a more precise description of the feature space, and then use some first-order statistics as feature vector. So these are the methods I wanted to present as for writer identification. And now I want to introduce shortly a database, because I want to show some results afterwards. And I use our data set because I have a result for most of the methods here. And we have 311 different writers. We have 1,609 images. All the images look like this. So we have a short text written. 1 page is in German, 4 pages are in English. Some writers have written 7 pages, so we have some pages left. And we use color images, but as you have seen, most of the methods are calculated on binarized images. And before I present the results, I want to say something about the evaluation methods, because it's somehow we need the identification and also the retrieval, and this should be covered. And there is, let's say, a quasi-standard currently. We generate one feature for each document image, so we have a couple of them. As I said, we have 1,600. We calculate a feature vector for each of these pages, which should describe the writing of the author. And then we calculate the distance. So we take one of these documents, calculate the distance to all the others documents, and then rank them according to the similarity, so according to the distance. And then we have 2 evaluation criteria. We have the soft criteria. At least one document image of the writer is included in the top K images. And we have the hard criterion. All documents have to be from the same writer. So I've illustrated it here. We have here the ranking, which is returned by the system. Green means this, so we have here 7 pages. Green means it's the same writer as the reference document. Red means it is a different writer. And so 1, 2, 4, and 5 are correct returns, and the others are wrong. And here we have the soft criterion, so for the top 1, which is actually the identification, because the system returns only one writer, and then we know the ID of the writer is fulfilled, since one document is from the same writer. The top 2 is also fulfilled, because one of those 2 documents is from the same writer. Top 5 is also fulfilled. Nevertheless, we have here one classification or wrong identification, because at least one is fulfilled, and the same is for the top 7. But for the hard criterion, top 2 we have fulfilled because both documents are from the same writer. Top 3 is not fulfilled, since the third document is from a different writer. and 4 is also not fulfilled because of the third document. So, and these are the results on a CVL data set, and as you can see, we are pretty high. So we have all 4 methods. So I have no results for the Bulaco method, but for the grid microstructure features, for the contour gradient descriptor, for the bag of words method, and also for the improved bag of words, the Fisher vector method. And as you can see, we are pretty high. So this is really the identification weight. So all methods are close to the 98%. Some of them are even above 99%. For the top 2 criterion, it's a little higher because one document has to be found only. And yeah, in average, for the soft criterion, the contour gradient descriptor has the best performance. But as you can see, the difference to the Fisher vector method is only quite small. For the hard criterion, it looks pretty much the same. So here, all documents which are returned have to be from the same writer. And as you can see, if we are at the CVL data set, we have 5 pages of a writer. So if we just take a look at the first 2 the system returns, then we are still above 95%. For the top 3, we are also above 90%. And for the top 4, which means that we want to get all the documents which have been written by the writer. So all of the documents have to be correct. And then you can see that the Fisher vector has nearly 90%. The contour gradient descriptor is slightly above 80%, and the others are a little bit worse. So what are the use cases for writer identification? So at least what we think, what are the use cases? And especially this example is for the writer retrieval. And so here the point is that we have unindexed documents. So we have just some pages which are written by someone, but we do not have any connections, they are not ordered, and so on. And then the handwriting is a good feature to say, okay, these documents belong together. And so if we make a ranking out of these documents according to the similarity, then we just usually get, for example, we take this as a reference document and the other documents are from the same writer, and we know that these may belong together and we can analyze them in more detail, and so we can cluster the documents again. The next thing, which is done in a different project of our institute, that was the case, they want to know who has written the document. So we have here some Glagolitic scripts. So Glagolitic is the oldest Slavic script, and those documents are from the 13th to 16th century. Those 2 documents have been written by the same writer. And as you can see, we have a lot of background noise going on and so on, because they were stored in 2 different locations. This one is stored in Innsbruck, this one was stored in Trento. And then we did also an evaluation on 306 documents of these with Glagolitic scripts, but only 7 writers. And still we were able to achieve an identification rate of nearly 99%. The next thing is, what it can also be used, writer identification, writer retrieval. It's also, as I said, free sorting of unknown documents. So we just have the idea that some documents may have been written by the same person, and using such a method we can pre-sort some documents and say, okay, we take a closer look at some of them because they are from the same writer. Although there are sometimes requests from documents by the same writer. Some modern application, for example, we have ransom letters and threat letters by the police, or also a connection between different archives. So if we want to know if this archive has also a text written by the same person. Another possibility, what is also the connection to the morning session, we can use it as a pre-processing step, for example, for handwritten text recognition. For example, we can just somehow say, okay, we have the writing style, we identify the writing style, and then we can apply the correct model to this handwriting for text recognition. So, as I said, writer identification is the task of identifying the writer. There is also writer retrieval, where we want to retrieve documents according to the similarity of the handwriting. On scientific data sets, we have usually an identification rate of above 95%. So here is really the crucial part of what I'm really looking forward in the READ project, because most of the scientific databases only have, let's say, 300, 400, 500 writers, and using really the data we can get from the READ project, we have thousands of writers, so it is really interested if all the method will work if there are a couple of thousand writers. And as I said, as for use cases, we can search for documents, we can cluster documents according to the similarity, we can do a pre-selection of documents, or we can do a pre-selection according to the writing style. And I think there are a couple of use cases where white identification can be used. Thank you.